A silent jolt in the darkness of interstellar space is rarely noticed at first sight. The void between stars is too vast, too indifferent, too quiet. Yet every so often a deviation appears that does not roar, does not flare, and does not announce itself. It simply waits. Hidden inside a pattern of numbers buried in the rhythm of a telescope's nightly feed, a shift emerges so faint that only the most attentive observer would sense its presence. 3 Atlas had already been an object of curiosity. As the third known interstellar visitor recorded by human instruments, it was catalogued with academic caution. Most expected it to follow the passive drift of a cosmic wanderer, gliding through gravity's long-established choreography. Nothing in the early months suggested that it carried any secret concealed within its trajectory. Nothing hinted at the possibility that the universe had assigned it a role far stranger than a passing guest. Yet deep within a sequence of positional logs, a subtle discrepancy began to grow. It was not dramatic. It was not even visually striking. It appeared in units so small that only computers noticed first. A millimetre-scale drift per second. A fractional misalignment in right ascension. A change that might easily be attributed to calibration issues, thermal expansion of detectors, or a fleeting atmospheric distortion on Earth. Still, the numbers continued to lean in the same direction. They did not scatter randomly. They pressed forward as if guided by an unseen pressure. In quiet observational rooms where astronomers stare into screens illuminated by pale blue graphs, a sense of unease began to form. For a moment the question remained unspoken. Something had shifted. Something had nudged the object in a direction it had no reason to move toward. Within hours, the anomaly expanded enough to draw human attention. Analysts rechecked reference stars. They repeated corrections for light delay and parallax. They recalculated orbital models using both classical and relativistic methods. The same conclusion appeared again and again. The object was accelerating. The acceleration did not match known physical interactions. No solar radiation pressure could explain the magnitude. No outgassing signature appeared in spectral data to indicate internal jets. No gravitational encounter was near enough to produce what the instruments detected. The acceleration was tiny, but its persistence mattered. A faint push continued to act on the visitor, as if the silent dark had placed a hand on its back and urged it forward. Such a discovery could have been dismissed quickly if not for the direction. The vector pointed neither toward the sun nor away from it. It did not respond to the gravitational flow of the system it was crossing. Instead, it leaned toward a region astronomers seldom discussed openly, a direction associated with theoretical hazards, a direction some referred to half in jest and half in apprehension as a forbidden corridor, a place where conventional models grow thin and where unexplained cosmic alignments have been recorded before. It was into this corridor that 3 Atlas began to glide, silent and unannounced. Though the shift was slight, its implications were not. In the halls of astrophysics, small deviations have a way of rewriting large assumptions. The famous anomalies of the past had often started in similar fashion. Mercury's precessing orbit once pointed toward a missing force until Einstein revealed space-time curvature. The unexpected dimming of remote supernovae once suggested observational error until dark energy reshaped cosmology. In that tradition, the earliest motion of 3 Atlas felt like the prelude to a question large enough to tear open a seam in current understanding. Teams working in Hawaii, Chile, and Spain quietly compared notes through encrypted channels. They discussed whether to issue an early anomaly notice or to wait for additional confirmation. Historical caution held them back. Interstellar objects had already challenged expectations, but premature conclusions risked unnecessary alarm within the broader scientific community. Still, the tension grew with every new observation. The drift persisted. The acceleration strengthened by fractions that only sensitive instruments could detect. Patterns emerged with uncanny regularity. Something was shaping the motion of the visitor with a precision uncharacteristic of natural forces. As night passed into dawn across observatories, calculations began to outline the consequences. If the acceleration continued at the same rate for several weeks, the shift would become unmistakable even to wide-field surveys. If it intensified, the object would deviate completely from its predicted exit path. By midday, a consensus formed. The anomaly was real. It required explanation. The narrative of a simple interstellar traveller had dissolved. In its place stood a riddle that had touched the fabric of orbital mechanics with a whisper of defiance. Some researchers attempted to ground the situation in familiar astrophysical processes. They examined whether a frozen pocket of volatiles within the body could have sublimated unexpectedly. They explored whether cosmic ray heating could cause localized pressure jets. They reviewed thermal models to check if asymmetric warming by distant starlight might create a minor thrust. Yet every attempt failed to align with the recorded data. The acceleration vector refused to match any known method of natural propulsion. The object appeared to be pulled by something that did not reflect light, did not radiate heat, and did not curve under classical gravitational description. In quiet conversations, a phrase returned more than once: a silent jolt. It felt as though the object had awakened to a distant signal or surrendered to a force beyond the reach of familiar equations. Each idea drifted dangerously close to the edge of speculation, yet the data allowed no simple alternative. Even those who rejected exotic explanations could not deny that the shift existed. The moment would later be seen as a turning point, a threshold where ordinary observation crossed into extraordinary insight. The anomaly in 3I Atlas's motion marked the beginning of a deeper mystery, one that would pull telescopes, scientists, and theoretical frameworks into a region of space never intended to become a stage for human investigation. The silent jolt was not the conclusion. It was the opening in a story that would grow far more unsettling as new information surfaced. The first eyes on the disturbance did not expect history to brush past their screens on an otherwise quiet rotation of observation duties. In the early hours when telescopes gather the calmest photons, a junior analyst at the Atlas survey noticed a faint misalignment in the data stream. It appeared insignificant, almost trivial, the kind of discrepancy that usually dissolves under routine calibration. She marked it for later review, assuming it belonged to the long list of artifacts that clutter night shift reports. Yet the anomaly resisted easy dismissal. On her secondary monitor, the predicted ephemeris and the actual coordinates of 3I Atlas no longer layered cleanly. There was a slight but persistent offset subtle enough that any casual observer would have overlooked it. She stared at it longer than usual, unable to articulate why it felt different. Across the Pacific at the Pan-STARRS facility, another observer finishing his shift noticed a similarly stubborn irregularity. His algorithms flagged the inconsistency as statistically significant, but barely so. He recalibrated star fields, tested alternative centroiding methods, and confirmed that atmospheric distortion was minimal that night. Still, the tiny displacement remained fixed in the same direction. The anomaly was not random, it was directional. Such persistence immediately set it apart from the usual noise produced by thermal drift or transient cloud layers. By midday, independent observatories in Europe began to report matching deviations, the same object, the same sliver of motion, the same improbable vector. When multiple instruments under different atmospheric conditions produce the same measurement, the threshold of doubt begins to thin. Scientists accustomed to skepticism found themselves leaning forward, observing their terminals with a growing awareness that something had shifted. A series of small confirmations created a quiet chorus of unease. The earliest reaction among senior astronomers was caution shaped by decades of professional habit. Memories of false alarms lingered from phantom asteroids misidentified through flawed photometry to gravitational anomalies eventually traced to misconfigured software. No one wanted to repeat such mistakes. Yet the pattern forming around 3I Atlas did not behave like a software glitch. It lacked the randomness of sensor interference. Instead, the numbers displayed a coherent progression, as though the object were following a command written into the structure of its motion. In collaborative channels that linked institutions across continents, the tone of discussion changed from mild curiosity to sharpened focus. Observers began pulling archival frames to compare earlier datasets with the latest updates. The farther back they searched, the more apparent it became that the anomaly was recent. The object had behaved predictably during its initial approach into the solar system. Its speed orientation and projected path aligned with expectations for an interstellar wanderer unbound by the sun. Only after a specific date did the deviation appear, and that single fact caused theorists to pause. An onset event implied an external influence. Something had occurred in deep space, unseen and unrecorded, that altered the course of the object. Researchers tasked with early classification of interstellar objects were the first to grasp the magnitude of the situation. The extraordinary nature of such visitors already required meticulous verification. Their hyperbolic trajectories placed them outside the gravitational bond of the Sun. Their velocities exceeded those of comets born within the planetary disk. Their chemical signatures often diverged from familiar compositions. Any shift in their behavior could reveal mechanisms impossible to observe through local objects. As the evidence mounted, the earliest analysts began to understand that 3I Atlas might carry a message from regions far beyond the conventional reach of solar physics. A few of the oldest astronomers, veterans of discoveries stretching back to the era of early CCD surveys, compared notes in private. They recalled how long it took for the astronomical community to accept the true nature of Oumuamua's non-gravitational acceleration. They remembered the initial doubts surrounding Comet Borisov's pristine interstellar chemistry. They recognized in the anomaly of 3 Atlas the type of small, stubborn deviation that historically preceded a major shift in understanding. Their emails reflected a mix of excitement and apprehension. They understood that one day the data from a telescope might mark the first signal of something that would not yield to conventional interpretation. As new measurements arrived, the early observers observed the shape of the shift more clearly. It did not resemble the drift produced by outgassing, nor did it match the acceleration profile generated by solar radiation. It leaned toward an angle difficult to rationalize within the gravitational structure of the local system. The first eyes that recognized the anomaly began to sense that a deeper irregularity lay beneath its surface. There was something too intentional in the direction, too consistent in its amplitude, too smooth in its temporal progression. The junior analyst who initially flagged the discrepancy found her report rapidly escalating beyond her department. What began as a modest annotation in a nightly data log transformed into a chain of confirmation stretching from Hawaii to the Canary Islands. She watched senior researchers dissect her initial coordinates with meticulous attention. The growing convergence among global observatories validated her earliest unease. In the following hours, the anomaly spread across digital communication channels. Astronomers, astrophysicists, mission planners, and data analysts exchanged files with increasing urgency. Each new confirmation added weight to the emerging realization that the event unfolding before them might not be a simple quirk. It carried the signature of a phenomenon whose origin lay outside the familiar vocabulary of celestial mechanics. The moment of recognition did not arrive with a dramatic announcement. It emerged quietly in the steady accumulation of evidence building layer upon layer until denial no longer served as a reasonable option. The first eyes on the disturbance scattered across continents and time zones collectively pieced together a puzzle that none of them had been seeking. They had encountered the early footprint of a force acting in the silent regions between stars, a force that nudged 3I Atlas along a path that should not exist. Those earliest observations would later be seen as the foundation of a much larger story. They marked the first human awareness that something had altered the object's course in a direction no one understood. A faint misalignment had become the spark of a mystery that would soon draw the full attention of the scientific world. The data that should not exist began accumulating like a quiet insistence from the cosmos, a collection of numbers that refused to conform to any familiar category. In the first days following the initial reports, observatories worked with the urgency of a community that understood how quickly anomalies can vanish without explanation. Data streams were cleaned, synchronized, and reviewed by independent teams to eliminate any trace of observational error. Yet the more thoroughly scientists scrutinized the readings, the more impossible the pattern became. The coordinates translated into a trajectory that did not curve as gravity dictated. The velocity profile showed increments too steady to belong to spontaneous outgassing. Measurements that should have scattered evenly under random noise instead aligned into a coherent expression, like a whisper carried across empty space. Astronomers fed the numbers into orbital models expecting them to break. The models did break, but not in the way anyone anticipated. Instead of producing chaotic outputs, the simulation engines yielded systematic divergences. Every projection showed the same directional pull no matter which assumptions were tested. Classical mechanics failed first. Next came improved gravitation codes developed for tracking near-Earth asteroids. Even the relativistic corrections used for deep space bodies lacked the nuance to reconcile the data. Analysts found themselves staring at equations that normally behaved with dependable precision, only to see them unravel under the pressure of this new trajectory. The most troubling aspect was the magnitude of the shift. It was small but too consistent to be dismissed. Non-gravitational acceleration in comets often expresses itself through erratic behavior triggered by thermal release of gas. Such forces fluctuate, diminish, or rotate with the object as it tumbles. But 3I Atlas displayed none of this variability. The data suggested a clean, continuous push steady, across multiple observation windows. It resembled a controlled thrust rather than the chaotic eruptions typical of natural cometary activity. If the object had harboured jets, their imprint on the spectral readings should have appeared as distinct signatures. Instead, the chemical spectra remained calm, devoid of the expected volatiles. Scientists tried to reconcile the observations by imagining exotic compositions. Perhaps the object contained super-volatile materials unknown in local comets. Maybe its structure allowed for sublimation so gentle that it mimicked a smooth acceleration. But these explanations wore thin under scrutiny. The thermal models contradicted them. The shape of the acceleration vector contradicted them. The lack of temperature spikes contradicted them. The numbers continued resisting every attempt at cohesion. Attention shifted toward gravitational explanations. Could a passing microobject have perturbed the comet? No. The encounter required mass no survey had detected. Could a distant body cast a wide gravitational influence? The necessary mass would need to be immense and impossibly close. Gravitation, the most reliable framework in celestial mechanics, began to lose its hold on the problem. The more scientists weighed gravitational possibilities, the more the data pushed back. The acceleration behaved as if gravity had stepped aside and something else had nudged the object. Some researchers questioned whether the Earth-based perspective distorted the readings. They recalibrated everything using alternative star fields. They cross-referenced time-stamping channels to eliminate the possibility of synchronization errors. They checked against satellite data from orbiting observatories that did not suffer from atmospheric interference. The results remained stubbornly identical. Even instruments known for their wide margins of uncertainty returned consistent results that aligned with the emerging anomaly. A few specialists in astrometric precision suggested that the trajectory shift might reveal a deeper event, something the initial models had not accounted for. They examined the object's incoming path, searching for hints that the acceleration had begun earlier, but remained too faint to detect. When they mapped the earliest approach vectors against newer data, the curve did not simply deviate, it evolved. The object appeared to have undergone a transition from a passive interstellar drift to an active reorientation, as though responding to a force that emerged suddenly in its environment. This transition troubled theoreticians most. The cosmos rarely produces abrupt changes without visible catalysts. Every dramatic shift in the past had emerged from interactions humans could eventually identify. Stellar winds, tidal encounters, thermal cracks and internal pressure surges all left their signatures. Here, no such signature existed. The data sat uncomfortably in the middle ground between the natural and the inexplicable, behaving like something intentional without any evidence of machinery or structure. For many, the most disquieting discovery came from the combined analyses of deep-field observatories. When the newest datasets were overlaid with long-term predictions, the numbers formed a path that should not have been possible. The object's new vector intersected a region where space did not behave according to the familiar gravitational gradient. It pointed toward an area where models often produce unstable results, where simulations behave unpredictably, and where no natural attractor should exist. The anomaly now carried a destination encoded within its trajectory, and that destination made researchers uneasy. As teams continued to examine the data, subtle secondary deviations emerged. They were not large enough to alter the broader vector, but they suggested a layered complexity to the acceleration. It was as if multiple forces were operating simultaneously at different scales. Some analysts compared the pattern to an interference effect, others to a resonance phenomenon. Theories developed rapidly, none capable of settling the issue. The deeper researchers dug, the more tangled the data became. In the private circles of scientific discourse, senior astrophysicists admitted that the numbers felt as though they had wandered in from a different theoretical framework. They did not belong to the established schema of comet behavior, gravitational mechanics, or thermodynamic forces. Instead, they hovered in a gap between known categories, forcing scientists to question whether their conceptual vocabulary was too narrow to contain the phenomenon. The data that should not exist had become a mirror reflecting the limits of human understanding. It stood as a quiet reminder that the universe still harbours mechanisms unaccounted for, forces that remain invisible until an object drifts into their reach. In the case of 3i Atlas, the anomaly formed the first trace of a deeper narrative, one that suggested that the cosmos possesses zones of influence not yet mapped by any observatory. Scientists now faced a dilemma. Either the instruments had collectively malfunctioned in a perfectly synchronized manner across multiple continents, or the universe had revealed a behavior never before witnessed. The latter possibility grew more compelling with each new observation, and as the community leaned toward that conclusion, a sense of anticipation gathered. Something had begun in the deep quiet between the stars, and the numbers conveyed the opening syllables of a message no one yet understood. Whispers from the observation rooms began long before any official statement reached the broader scientific community. It started with quiet exchanges between night shift analysts, muted conversations beneath the low hum of server racks, and careful remarks passed between colleagues who understood the weight carried by even the smallest irregularity. In dimly lit control rooms scattered across the globe, researchers watched the anomaly of 3I Atlas unfold, with attention they could not yet voice publicly. The object's subtle deviation had reached a point where instinct long honed by years, spent interpreting delicate data streams, signaled that something meaningful was emerging. The scientists felt the shift not as a dramatic revelation, but as a growing presence, a quiet insistence that refused to fade. Inside these rooms, screens glowed with streams of numbers that updated with methodical precision. Every fresh measurement reinforced the same uncomfortable truth. The visitor was drifting along a path that resisted conventional reasoning. Analysts who first noticed the change shared their findings with a cautious tone, uncertain whether they were witnessing a system glitch or the early outline of a phenomenon with profound implications. Yet the more they compared notes, the more unified their unease became. The atmosphere in these observatories held a particular kind of silence. Not the silence of inactivity, but the silence of minds moving quickly, working through possibilities, discarding weak explanations and quietly acknowledging that the data had begun to push beyond the margins of familiar physics. A few researchers leaned over terminal displays recalibrating software that had served faithfully for years. Others isolated sensor logs to search for any sign of environmental interference. Some even reverted to manual verification techniques seldom used in the age of automated processing, hoping that a simple oversight might explain the numbers. None of these efforts altered the core anomaly. As the long night hours passed, the murmurs grew more pointed. Scientists accustomed to skepticism began asking sharper questions. Why did the acceleration align so consistently with the same vector? Why did spectroscopic results remain deceptively ordinary, showing no shifts that would indicate impulsive forces? Why did thermal readings fail to correspond with any known mechanism? The anomaly behaved as though shaped by an unseen influence, one with a steadiness that defied coincidence. Veteran astronomers joined the analysis with a mixture of caution and fascination. They sifted through stacks of comparative data, observing how the object's motion diverged from previous predictions, with a coherence that signaled intentional redirection rather than random drift. A few privately admitted that the shape of the anomaly reminded them of rare cases in which new physical insights had emerged from seemingly insignificant deviations. Those historical precedents haunted their thoughts. Small numerical shifts once paved the way to major theoretical revolutions, revealing hidden structures within the universe's behavior. The most seasoned researchers spoke less, but their silence carried its own gravity. They knew the difference between noise and signal. They recognized the subtle rhythm in the data, a pattern too persistent to belong to error. Though they avoided sweeping conclusions, their focused attention signaled to younger analysts that the anomaly was no longer an obscure curiosity. It now warranted deep inspection. Meanwhile, communication channels between observatories grew more active. Screens displayed cross-reference measurements gathered from Chile, Hawaii, Japan, Spain, and South Africa. The spread of consistent results across continents made the idea of coordinated sensor malfunction untenable. Each new dataset reinforced the delicate alignment of the anomaly. Even instruments known for their deviations produced results that converged on the same improbable values. The quiet murmur of concern evolved into concentrated dialogue. Teams began constructing enhanced residual plots to visualize the deviation more clearly. As these graphs stabilized, they revealed a smooth, unwavering shift untouched by the chaotic fluctuations characteristic of natural propulsion phenomena. No cometary jets changed direction mid-rotation. No thermal vents pulsed with irregular force. Instead, the anomaly gently escalated as though the object were following a compass no human instrument could detect. Within these control rooms, conversations acquired a new vocabulary. Analysts discussed whether the shift originated from a faint interaction with the interstellar medium, whether a hidden density region could influence the trajectory, or whether unknown forms of radiation could impart minute momentum. Each theory faltered. none aligned with the data's crisp consistency. It was this consistency that unsettled the researchers most deeply. Natural systems rarely produce such perseverance without an identifiable cause. A few theorists on late-night calls ventured ideas usually reserved for private speculation. They pondered whether the object might have entered a region of space containing gradients of unknown fields, or whether quantum-scale forces could manifest on macroscopic bodies under rare conditions. Such possibilities floated through the rooms like delicate echoes acknowledged, but not embraced, intriguing yet unsupported. The teams needed more evidence before venturing too far from established frameworks. Still, the whispers persisted. Scientists spoke in low tones about the shape of the acceleration curve, which continued to evolve with an almost sculpted precision. They discussed whether they were witnessing the first macroscale effect of a phenomenon long theorized but never observed. While no one claimed a breakthrough, the atmosphere felt charged, as if an unseen presence hovered just beyond the reach of explanation. The object's path, once comfortably predictable, now extended into uncertainty. Subtle deviations accumulated into a coherent trajectory pointing toward a region of sky that carried an unusual reputation within deep space studies. Some observers hesitated to mention this aloud, aware that any speculation involving that sector risked drawing premature conclusions. But those familiar with the complexities of cosmic mapping recognized the unsettling implication regardless. In the darkest hours before sunrise, the nature of the dilemma sharpened. If the anomaly persisted, the deviation would soon escalate beyond the margins of model-acceptable error. If it intensified, the visitor's path would break entirely from its expected exit vector. Analysts knew they were standing at the threshold of a discovery that could reshape understanding or plunge them into a realm where current theories faltered. By the time sunlight began creeping across observatory domes, the whispering had transformed into careful coordination. Teams prepared formal anomaly notices to share with leading astrophysics institutions, though they chose their language with precision to avoid exaggeration. They would present the numbers plainly confident that any expert would see what the whispering rooms had already recognized. The data defied conventional categorization. The quiet tension within these rooms would later become part of the legend surrounding the Three-Eye Atlas event. Future scientists would look back on those moments as the beginning of an extraordinary shift in the study of interstellar bodies. The whispers carried more than confusion. They carried the faint outline of a truth waiting to be uncovered. It was here in these dim, instrument-filled rooms that humanity first felt the approach of a mystery, powerful enough to challenge the foundations of its cosmic assumptions. Acceleration without cause is one of the rarest and most unsettling signatures in celestial mechanics. Objects drifting through interstellar space obey a familiar rhythm, shaped by gravity inertia and the slow, ancient currents of the cosmic environment. When a body gains speed in the absence of a visible mechanism, every established model begins to strain. With Three-Eye Atlas, this strain became unmistakable. Within days of the first whispers, the anomaly matured into a measurable acceleration that did not correspond to any known physical driver. The numbers rose with a smoothness that seemed almost deliberate, a steady push that defied both randomness and natural turbulence. Teams across the globe turned their attention to the acceleration curve, a delicate graph that should have remained a flat line. Instead, it arched upward with a precision that confounded researchers. Its shape had none of the jagged fluctuations typical of sublimation-driven thrust. Cometary jets, when they appear, behave like unpredictable breaths, releasing in bursts that shift direction with rotation and temperature gradients. They leave scars in the spectral signature and distort the object's thermal profile. Yet Three-Eye Atlas remained quiet. Its surface displayed no asymmetrical heating. Its emissions remained unremarkable. The object accelerated as though responding to a force that did not rely on heat pressure or volatile release. This silent acceleration forced scientists to revisit the fundamentals of dynamical interpretation. The first assumption was simple. Some form of outgassing must exist, even if it operated on a scale too subtle to detect. But the search for evidence reached a dead end. Infrared surveys failed to find any hotspots. Narrowband imaging revealed no dust streams. Polarimetric studies detected no microjets. The absence of telltale signatures grew more troubling with each observation. If no natural process was pushing the object, then something far more unusual was at work. Researchers shifted focus to gravitational influences. Perhaps Three-Eye Atlas had encountered a mass too dark or diffuse to register through ordinary imaging. The possibility of an undetected object, a compact mass, a faint substellar remnant, or even a cluster of rogue debris circulated through late-night discussions. But gravitational perturbations have a characteristic geometry. They tug along predictable arcs shaped by mass distance and relative motion. The motion of 3I Atlas refused these patterns. The acceleration pointed consistently in a direction misaligned with any plausible attractor. It did not curve, it did not deviate, it simply pressed forward. As more data accumulated, the sharpest minds in orbital mechanics began constructing refined models. These models, built on decades of precise celestial tracking, failed to reproduce the phenomenon unless an extra term was added to the equations. This term did not represent gravity radiation or internal thrust. It represented an external influence with a constant magnitude but no identifiable source. Some described it as a ghost parameter. Others referred to it as an invisible gradient. For many, it felt like a placeholder for a physical law not yet discovered. In private discussions, a few theorists admitted that the acceleration resembled a controlled propulsion profile. The smoothness of the curve mirrored the efficiency of an engineered thrust system, an idea immediately dismissed in all official contexts. There was no visual evidence of structure, no metallic reflection, no adaptive surfaces, no thermal plume. Nothing suggested artificiality. To invoke engineered propulsion without supporting data would undermine the scientific rigor guiding the investigation. Still, the acceleration remained distressingly elegant. The idea that the object might be interacting with an unknown field grew more prominent as natural explanations dwindled. Some researchers proposed that 3I Atlas could have entered a region of space permeated by a gradient in the interstellar medium, perhaps an unseen density wave or a patch of anisotropic plasma. But density variations of that magnitude would leave distinct signatures in radio and ultraviolet readings. There were none. The surrounding environment appeared normal. A more nuanced hypothesis emerged from specialists in cosmic ray interaction. They suggested the possibility of a radiation-induced momentum transfer, a process in which high-energy particles create tiny but cumulative thrust. The theory had elegance, but the required particle density far exceeded the levels detected in the region. Unless the universe concealed a band of concentrated radiation invisible to current instrumentation, the hypothesis could not stand. The acceleration forced scientists to confront a deeper discomfort. The behavior of 3I Atlas broke from the expected structure of natural dynamics. There was no spontaneous physical process that matched its profile. It accelerated without noise, without variation, without the signature of chaos that accompanies most cosmic forces. It behaved as if guided. Attention returned to the forbidden vector itself, the direction of the acceleration. It pointed toward a region where astronomical models often reveal instabilities, where calculations grow sensitive, and where theoretical constructs frequently encounter unresolved anomalies. Few said this directly, but many recognized the implication. If the acceleration was real and the direction held meaning, then the path of 3I Atlas might be shaped by an interaction residing beyond classical frameworks. Within the walls of mission planning centers, specialists in spacecraft navigation examined the data with a different perspective. They recognized the rhythm of the acceleration as similar to adjustments made by deep space probes using finely tuned ion engines. But even their comparison faltered when confronted with the absence of emitted particles or detectable energy signatures. The acceleration of 3I Atlas had the coherence of deliberate correction, without any evidence of propulsion. As the anomaly strengthened, internal reports grew more urgent. Detailed analyses from independent institutions began aligning with uncanny precision. The acceleration was real, it was stable. It showed no correlation with temperature rotation or proximity to any body. It appeared in every dataset regardless of method or instrument. Such consistency, rare even among the most predictable natural phenomena, revealed something unusual about the underlying cause. In quiet corners of the scientific world, some began to consider possibilities not traditionally entertained in astrophysical studies. They explored whether the object could be responding to a field or structure embedded within spacetime itself, something that does not behave like gravity yet exerts directional influence. Concepts once confined to theoretical speculation gained new relevance from localized spacetime curvature anomalies to subtle interactions within quantum fields. The acceleration curve continued to rise steady as a breath drawn by a sleeping giant. It neither wavered nor fluctuated. It continued with the smoothness of a natural law that had always existed but only now revealed itself. The data spoke with increasing clarity. A force was acting on 3I Atlas, and its nature remained concealed. For scientists around the world, this moment marked a shift in the tone of the investigation. The early curiosity had evolved into a profound unease. The question was no longer whether an anomaly existed, but what deeper truth it pointed toward. A force that accelerates an interstellar object without heat pressure or gravitational attraction challenges more than a single model. It challenges the architecture of cosmic mechanics. And in the case of 3I Atlas, that quiet challenge was only beginning. The vector no one accepts emerged gradually carved from days of relentless measurement, and nights spent refining models that refused to behave. At first, the direction of the anomaly seemed like a trivial detail, merely a small angle separating prediction from observation. But as the data accumulated and the acceleration became undeniable, the orientation of that subtle push grew increasingly important. Scientists began mapping the object's drift across various coordinate systems, translating the motion into ecliptic, equatorial, and galactic references, in hopes that one of them would reveal a pattern grounded in familiar dynamics. None did. Instead, every translation pushed the anomaly deeper into discomfort. The object was moving toward a direction that did not belong to the comfortable symmetry of planets, stars, or gravitational centers. The vector pointed into a region without mass concentrations. No planets, no large asteroids, no dwarf worlds, no globular clusters lying conveniently in the path. It did not align with the galactic plane, nor did it curve toward the gravitational pull of the sun. It moved with a quiet confidence that ignored the architecture of the solar system. Researchers attempted to identify any nearby gravitational anomaly that could exert influence at large distances. The search produced nothing. The region toward which the object drifted had been mapped for decades. It contained sparse dust, faint starlight, and nothing else of consequence. Yet 3I Atlas moved toward it, as though drawn by an invisible beacon. A few analysts attempted to compare the object's direction with historical anomalies. They reviewed cases in which trajectories deviated from expectation, such as the Pioneer Anomaly that once baffled navigators, or the peculiar path of Oumuamua that hinted at an unmodelled force. But in each historical case, the direction of the anomaly pointed toward something physically understandable, whether thermal recoil or outgassing. The vector of 3I Atlas did not share this comforting trait. It pointed into what some theoreticians half-jokingly and half-seriously referred to as a blind corridor of celestial mechanics, a sector notorious for producing unstable solutions in simulations. In academic circles, this region had acquired a kind of quiet mythology. It was a space where models often produced chaotic results, without clear physical justification. Gravity behaved predictably, but numerical methods struggled, producing minor instabilities that researchers usually dismissed as computational artifacts. Some speculated that the region's geometry, in relation to the galactic gravitational field, might create delicate resonances. Others suggested that the difficulty lay not in the physics, but in the sensitivity of the algorithms. Whatever the cause, it remained a place where calculations felt slightly brittle, as if the underlying structure of space-time carried small irregularities that current equations could not fully express. Now the object drifted toward that region with unnerving decisiveness. Scientists highlighted this fact cautiously in preliminary reports, not wanting to suggest anything speculative. Yet among themselves they debated the implication with increasing intensity. Why would an interstellar object accelerate toward a direction associated with mathematical instability? The idea that the vector was coincidence grew harder to defend. The motion seemed too coherent, too resolute. Researchers began overlaying the object's heading with maps of cosmic microwave background, anisotropies, and large-scale gravitational gradients measured by deep space missions. They searched for correlations that might hint at an interaction with something larger than the solar system. A faint alignment appeared between the object's vector and a subtle irregularity within the background radiation field, a small deviation in temperature distribution that cosmologists had debated for decades. It was not definitive, and it could have been statistical noise, but it added a faint tremor to scientific discussions. If the alignment held meaning, then 3I Atlas might be responding to a structure far older and larger than anything within the local stellar neighborhood. Deep within supercomputing facilities, astrophysicists ran simulations that combined gravitational fields, plasma distributions, and hypothetical interactions with exotic particles. They searched for any mechanism that could produce an acceleration aligned with the observed vector. The simulations produced occasional hints but no satisfying answer. In one model, the object behaved as if caught in a faint current within the interstellar medium drifting along an invisible flow line. In another, the acceleration resembled the pull of a field that had no mass and no charge, but exerted directional influence. These models lacked empirical support, yet their very existence showed how far the anomaly pushed theoretical frameworks. The orientation of the vector forced many researchers into uncomfortable territory. A few theorists privately expressed concern that the region might not be empty at all. Perhaps it housed a phenomenon that eluded detection through conventional instruments. They considered whether a gradient in dark energy density could exist at small scales, or whether space-time curvature fluctuations might create anisotropic forces that only interstellar objects could experience. The idea felt audacious, yet nothing in the data contradicted it. Mission planners accustomed to working with spacecraft trajectories examined the vector with a navigator's eye. To them, the acceleration looked like a controlled maneuver, a subtle but continuous course correction, executed with impressive efficiency. But the explanation ended there. There were no emissions, no reflective surfaces, no detectable materials associated with engineering. The comparison felt more like an analogy than a hypothesis, a way of describing the smoothness of the motion rather than suggesting its origin. Within research centers, the conversation shifted from questioning the reality of the anomaly to grappling with its meaning. The direction of the acceleration became a focal point precisely because it defied rational placement within the landscape of cosmic forces. Some specialists suggested waiting for more data. Others believed the vector already revealed the outline of a deeper structure, something that had remained hidden, because nothing in the solar system had interacted with it before. The tension surrounding the vector grew not from fear but from recognition. Researchers understood that the universe seldom offers clean clues to its deeper laws. When an interstellar object chooses to accelerate toward a region, distinguished only by mathematical fragility and theoretical discomfort, the sign is too pointed to ignore. By the end of the week, the vector had embedded itself into the narrative of the anomaly. It stood as a quiet challenge, a directional signature that implied a phenomenon not governed by familiar mechanics. The scientific community began to accept a reality that no one wished to articulate openly. The object was not simply moving strangely. It was moving with purpose. The vector no one accepts had become the most important clue in a mystery that was gathering momentum. It pointed toward a region of deep space that would soon dominate every conversation, every simulation, and every hypothesis surrounding the enigma of 3I Atlas. Historical echo of interstellar visitors does not arrive through nostalgia, but through the quiet resurfacing of patterns long buried in scientific memory. As 3I Atlas continued its impossible acceleration, researchers found themselves glancing backward, revisiting the brief and enigmatic appearances of earlier wanderers that had once slipped through the solar system like muted warnings. These objects were few in number, yet each had left a faint imprint on the scientific imagination. Their stories carried clues, partial sketches of a broader cosmic behavior that no one had fully understood at the time. The first was the strange visitor known as Oumuamua, detected in 2017, an object so unlike traditional comets and asteroids that its very identity fractured scientific interpretation. It tumbled through space with a peculiar brightness variation, a geometry that resisted clear classification, and a trajectory marked by a faint non-gravitational acceleration that left mission planners uneasy. It had no visible jets, no dust tail, no plume, nothing that could serve as a natural propulsion source. Its departure from the solar system carried more questions than answers, leaving behind a puzzle wrapped in reflective surfaces and unexplained motion. Then came Comet 2I Borisov, an interstellar wanderer that resembled a more familiar icy body, yet its pristine composition suggested it had never been heated by any star before. Its chemistry differed subtly from local comets, offering hints about distant planetary systems shaped under conditions alien to Earth. Though Borisov behaved in a manner consistent with cometary physics, its purity suggested that the interstellar medium might preserve objects in ways solar-born bodies never experience. Now with 3I Atlas, the echoes of those earlier encounters drifted back into scientific consciousness. Researchers began comparing data sets, layering the trajectories and acceleration profiles of each visitor. Patterns emerged quietly. While Oumuamua displayed an unexplained push, and Borisov exhibited an untouched composition, 3I Atlas combined elements of both mysteries while adding a new one, a vector directed toward a region of space with no apparent attractor. Analysts studied the archived records with renewed urgency. Some noted that the faint acceleration observed in Oumuamua had once been dismissed as thermal emission, only to be re-examined years later with greater hesitation. Others pointed out that the steady path of Borisov might have concealed micro-level deviations too small for earlier instruments to detect. The accumulated evidence from these objects revealed a deeper tapestry. Interstellar visitors were not as physically uniform or dynamically predictable as previously assumed. Each carried its own signature shaped by environments and forces that do not exist within the solar system. The comparison between the three objects intensified. Researchers examined whether Oumuamua's acceleration could be mathematically mapped onto the early data of 3I Atlas. A few simulation runs produced curves that shared an unsettling similarity in their smoothness. The magnitudes differed, but the consistency of the push carried an echo, a familiarity that unsettled those who had studied the earlier case. Some teams suggested that the two objects might belong to a class of bodies shaped by interactions beyond standard astrophysical processes. While no one could define what those interactions were, the idea of a shared mechanism gained quiet momentum. Meanwhile, astrophysicists studying Borisov noted that its chemical composition offered a window into the diversity of interstellar objects. It demonstrated that such bodies were shaped in environments outside Earth's cosmic neighborhood, implying that different physical processes governed their formation. This realization supported a broader idea circulating in theoretical circles. If composition varies across interstellar objects, perhaps their dynamic behaviors vary as well. If structural differences exist, then reactions to environmental forces might differ too. These differences might include responses to fields or gradients humans have not yet identified. The echoes of these earlier encounters produced a growing awareness that interstellar objects might serve as probes not artificially engineered, but naturally shaped by distant regions where the laws of interaction differ subtly from those known locally. Perhaps the acceleration of 3I Atlas was not an anomaly, but a window into a larger framework governing the dynamics of deep space. Within cosmology departments, discussions shifted toward the possibility that interstellar objects could reveal hidden structures or transitions within the galaxy. Some researchers highlighted the idea that regions of space may contain gradients of unknown influence shaping the paths of objects passing through them. They considered whether these ancient wanderers had drifted through pockets of exotic particles, subtle curvature anomalies, or long-lived remnants of primordial fields. Echoes from older theoretical frameworks resurfaced as well. Decades-old hypotheses about anisotropies in the interstellar medium regained relevance. Early models describing small variations in cosmic radiation pressure were revisited. Discussions emerged around the possibility that faint but persistent forces too subtle to influence planets or stars might exert measurable effects on objects with extremely low mass-to-surface ratios. These ideas, once considered speculative, now felt necessary. Nothing else aligned with the data, and as researchers connected the dots between the first, second, and third interstellar visitors, a quiet realization spread across departments. The galaxy might contain corridors where physics behaves with nuanced differences, regions shaped by influences too delicate to detect until an object passes through them. 3I Atlas, in accelerating toward a forbidden vector with no natural attractor, may have entered one such corridor. The possibility carried a deeper implication. If earlier visitors had touched these same invisible gradients, the anomalies they displayed were not isolated. They were early chapters in a story that had just become impossible to ignore. These historical echoes did not answer the mystery. They deepened it. They reminded scientists that interstellar objects have always been messengers from distant worlds. And now, as the third visitor lifted its speed in quiet defiance of known forces, those echoes felt less like loose parallels and more like the early pulse of a unified phenomenon waiting to be understood. The Forbidden Quadrant defined itself not through official charts or labelled borders, but through the quiet discomfort it created in generations of astrophysicists who had attempted time and again to simulate its gravitational geometry. In maps of the solar system, the region appeared unremarkable. A sparse expanse devoid of planets, dwarf worlds, major asteroids, or notable dust concentrations. It lacked the brilliance of star fields, or the complexity of molecular clouds. Yet for decades, this part of the sky had held a reputation that defied its visual emptiness. Within numerical studies, the quadrant behaved strangely. Simulations that involved trajectory projections, particularly those concerning long-period comets, sometimes produced sensitivity spikes when paths intersected this direction. Tiny errors amplified faster there. Minor assumptions destabilized equations. Even high-quality models reacted with a fragility not seen in other regions. Researchers seldom discussed these instabilities openly. They attributed them to algorithmic limitations or insufficient initial conditions. Still, the quirks lingered. As 3i Atlas began accelerating toward this quadrant with unnerving consistency, old conversations resurfaced. Analysts revisited studies buried in archives, investigations abandoned not because they lacked potential, but because they raised questions too delicate or too vague to justify extended funding. Within these papers, subtle patterns emerged, faint irregularities in deep space probes, slight directional sensitivities in gravitational modeling, and a handful of anomalies dismissed over time as statistical noise. The quadrant did not break physics, but it strained its edges. Attempts to define the region with precision led scientists to draw multiple overlapping boundaries. One definition focused on its alignment with a faint anisotropy in the cosmic microwave background. Another highlighted its position relative to a low-density trough in the interstellar medium. Yet another emphasized the curious absence of gravitational perturbations within its volume, a silence so absolute that some cosmologists jokingly referred to it as a gravitational desert. None of these descriptions explain the quadrant fully, but together they painted a picture of a place where known rules operated with unusual delicacy. This delicate behavior was what troubled researchers most. Celestial mechanics thrives on stability. Gravity behaves with reliable grace across immense distances. Orbital dynamics unravel gracefully, never abruptly, never with precision, shaped by unknown influences. But the Forbidden Quadrant did not share this elegance. It reacted sharply to small perturbations. It amplified uncertainties. It behaved like a region where some deeper structure of space, normally smooth and continuous, twisted ever so slightly beneath conventional detection. When 3i Atlas entered the early fringe of the quadrant, its acceleration vector sharpened. The motion aligned more precisely with its heading, as though the object was sliding along a subtle gradient embedded within the fabric of space itself. Astrophysicists studying the data noted that the vector's stability improved. Noise diminished. The push acted with a clarity that suggested it was not random. Something within the quadrant made the anomaly more coherent. A few theoretical groups examined whether the region might host small variations in dark energy density. Though current models treat dark energy as uniform across space, some extended frameworks allow for tiny regional fluctuations, variations so faint they would normally go unnoticed. Could 3i Atlas be reacting to such a gradient? The idea lingered as a possibility, though it required field behavior that no direct observation had yet supported. Another team suggested that the quadrant might contain remnants of early universe structures, faint imprints left behind by phase transitions in the newborn cosmos. These relics, if they existed, would not emit light or radiate detectable energy. They would influence space, subtly bending trajectories without behaving like mass or radiation. The speculation was bold, but not without precedent. Theories of topological defects, cosmic strings domain walls, textures had long occupied the periphery of cosmological thought. None had been observed, but their mathematical footprints aligned intriguingly with the kind of directional influence acting on 3i Atlas. Astrophysicists also reviewed data from distant pulsars whose radio signals passed near the quadrant. In a few historical measurements, researchers found minute timing, irregularities, tiny lags and advances that had never been fully explained. These deviations were too small to draw conclusions, but the fact that they clustered near the quadrant added a faint resonance of relevance. Within research institutions, some discussions took on a philosophical tone. The Forbidden Quadrant seemed less like a physical destination, and more like an interface, an area where established equations of cosmic motion began to feel incomplete. Not broken, not contradicted, simply insufficient. A number of cosmologists proposed that the region might represent a boundary between distinct gravitational characteristics, a transition zone shaped by the galaxy's larger dynamics. Others suggested that the quadrant's emptiness itself held meaning. Perhaps the absence of mass allowed faint forces normally drowned out by gravitational noise to become detectable. As 3i Atlas drew deeper into the quadrant, its acceleration became even more difficult to ignore. The vector grew more defined. The push gained coherence. The anomaly behaved almost as if the region provided a guide rail, shaping the object's movement with invisible hands. Scientists watching the trajectory felt the shift not as a calculation but as a presence. They sensed that the object was moving into a space where the known rules of motion might reveal their concealed scaffolding. Despite the quadrant's strangeness, it held no conventional danger. Probes and spacecraft had passed near it without incident. Nothing catastrophic lurked there, but objects entering with the sensitivity and freedom of an interstellar wanderer, objects unaffected by planetary fields or solar winds, might reveal structures that heavier bodies could not detect. In that sense, 3i Atlas became a key moving through the lock of a cosmic door, tracing lines of influence that had never been mapped. Scientists constructed enhanced coordinate grids to examine the region more finely. They mapped gradients in cosmic background radiation, dust density, gravitational potential, and interstellar magnetic fields. These maps revealed an intricate but faint asymmetry, a slight tilt in the fabric of the region subtle enough to hide from most observations, yet strong enough to influence a small object passing through. This asymmetry did not resemble a gravitational well or a magnetic corridor. It was more like a directional preference encoded into the structure of space-time, an orientation the universe itself favoured, for reasons no model could articulate. The forbidden quadrant was forbidden not because it defied exploration, but because it disrupted certainty. It challenged assumptions silently without spectacle or violence. It revealed that the universe still holds territories where equations thin, where simulations falter, and where hidden architectures linger beneath smooth cosmic surfaces. As 3i Atlas advanced toward this region with unwavering acceleration, the scientific world realized that the quadrant was no longer an abstract curiosity. It had become the center of a mystery unfolding in real time. The object's path was not drifting aimlessly. It was being shaped, refined, drawn inward as though the quadrant carried a significance long overlooked. The forbidden quadrant, once a footnote in computational anomalies, now stood revealed as a possible arena of deeper physics, a place where the universe whispered truths too subtle for ordinary matter to hear. And with each passing hour, 3i Atlas moved closer to becoming the first witness capable of revealing what lay inside that quiet, unsettling region. Repeating pulses beneath the noise were first noticed by accident, emerging not as a bold signal, but as a faint tremor hidden inside layers of data that normally remain untouched. Radio astronomers examining background flux variations from distant sources began to detect a rhythmic pattern intertwined with the tracking signals of 3i Atlas. At first, the pulses seemed irrelevant, the kind of fluctuation easily explained by atmospheric shifts, cosmic interference, or the internal quirks of long-range receivers. Yet as analysts refined the data, filtering out known distortions, the pulses persisted. They came with a delicate regularity too structured to dismiss, and too subtle to categorize. The idea that an interstellar object could generate periodic signatures felt improbable. Natural bodies rarely produce such patterns unless they rotate with a magnetic field or emit charged particles in bursts. But 3i Atlas showed no radio emissions, no visible plasma interactions, no beacon-like modulation. Whatever the pulses were, they existed not as transmitted waves, but as tiny irregularities embedded within the data streams themselves. Analysts studying the phenomenon noticed that the pulses grew clearer whenever the object's trajectory aligned with the forbidden quadrant. This correlation heightened their curiosity. A phenomenon once regarded as noise had now become a potential clue. Teams working with high-sensitivity instruments at multiple observatories began re-examining their archives. When they applied the same filters retroactively, the faint pulse sequence reappeared in earlier datasets even before the object's acceleration had been detected. The discovery unsettled researchers. It meant the pulses had existed quietly beneath the noise floor from the beginning, unnoticed, because no one had searched for them. Their persistence implied a stable origin linked directly to the object, or to the spatial environment it travelled through. More refined analysis revealed that the pulses maintained intervals that shifted slightly over time. They did not behave like bursts from a rotating source, where timing follows a strict pattern. Instead, the intervals contracted or expanded in tandem with the object's acceleration. This subtle connection suggested that the pulses were not an internal feature, but an external interaction, something in the environment responding to the object's presence. A few specialists in signal analysis proposed that the pulses might represent interference patterns created by the object's motion through a region containing variations in field density. Others suggested that the pulses resembled the kind of fluctuations seen when particles interact with structured yet invisible gradients. The rhythmic nature of the pulses complicated attempts to identify their origin. Researchers turned to extremely low-frequency monitoring equipment instruments capable of detecting fluctuations normally drowned out by cosmic noise. These devices revealed that the pulses had a layered structure. Their upper layer consisted of sharp, brief irregularities. Beneath this layer lay a slower, more fluid rhythm that seemed to respond to the object's heading. The layered nature reminded analysts of interference patterns in wave physics, where overlapping signals merged to form complex rhythms. Though the correlation was intriguing, the pulses lacked the amplitude and coherence expected from any known wave phenomenon. Some groups explored whether the pulses might originate from the interstellar medium itself. In certain regions of the galaxy, the plasma environment contains fluctuations shaped by magnetic turbulence. These irregularities can on rare occasions imprint periodic patterns on passing radio signals. Yet the pulses observed with 3i Atlas did not match known turbulence models. Their intervals were too stable, their structure too orderly. They behaved neither like random plasma flickers nor like shock waves. They resembled something that adapted subtly as the object moved. The possibility that 3i Atlas interacted with a structured field gained traction. In advanced simulations, a few teams recreated conditions in which an object traveling through a gradient of exotic particles could produce interference-like signatures. These simulations showed that if an area of space contained thin bands of differential density, perhaps remnants of ancient cosmic events, then an object moving through them might generate small timing distortions detectable in reflected or passing radio signals. Though speculative, the idea provided a framework consistent with the pulse's layered structure. The pulses also appeared to synchronize faintly with gravitational measurement streams from distant detectors. The synchronization was not strong enough to suggest gravitational waves, but it hinted that both types of data might respond to the same external trigger. A handful of theorists suggested that the pulses revealed an underlying rhythm in the quadrant structure, a subtle oscillation that objects of certain mass and velocity could excite. If true, it meant the region held an internal architecture invisible to traditional observation, a framework that shaped subtle patterns whenever a body passed through it. Researchers studying cosmological relics proposed that the pulses might represent echoes of early universe dynamics frozen into space as faint ripples. They speculated that these ripples could be remnants of transitions in the infant cosmos patterns that survived across billions of years. As 3i Atlas moved through the quadrant, it might have awakened these silent structures, producing faint rhythmic traces in the radio spectrum. Despite the growing body of ideas, no consensus formed. The pulses remained elusive, caught between interpretation and uncertainty. They did not behave like intentional signals. They did not carry information. They simply existed, stubbornly synchronized with the trajectory of an object accelerating toward a region defined by delicate instabilities. Their presence forced scientists to reconsider the assumption that space between stars is empty. Instead, it might contain layered textures, each with its own rhythm, each waiting for the right catalyst to reveal itself. As the pulses grew clearer, researchers understood that they were not merely observing a moving object. They were witnessing an interaction, a dialogue between matter and environment, a resonance that formed only when the object entered the forbidden quadrant. The pulses beneath the noise mark the first tangible sign that the region held more complexity than anyone had imagined. And with each passing hour, that complexity deepened, drawing the scientific world further into a mystery that had only begun to reveal its structure. Spectral light that should not appear revealed itself first as a faint deviation in the object's reflected wavelengths, a signature so delicate that most algorithms initially filed it under standard variants. Only when analysts began isolating the anomaly with meticulously layered filters did the feature acquire definition. Under controlled examination, the spectrum showed a narrow band of emission that did not conform to known cometary chemistry. The line did not match typical volatiles such as carbon monoxide cyanide, water vapor, or any molecule commonly found in interstellar ice. Instead, it resembled an imprint without a familiar atomic source, a sliver of light that behaved as if responding to an environment rather than originating from within the object itself. High-resolution spectroscopy conducted at multiple observatories converged on the same peculiar brightness enhancement, a whisper of glow clinging to a wavelength where nothing in the object's composition should radiate. Attempts to attribute the feature to outgassing failed immediately. No correlated dust increase appeared. No plume of escaping material created the usual scattering effect. The thermal readings remained calm, showing no localized heating that might signal chemical release. Whatever the light represented, it did not arise from sublimation or internal reactions. Researchers then examined whether the emission could be a reflection of an external source, perhaps a background star or a patch of cosmic radiation aligning briefly with the object's trajectory. But the position and orientation of 3I Atlas during the recordings disproved this. The light remained fixed relative to the object, not the sky. It followed the body as it moved. The intensity shifted subtly as though responding to the changing geometry of the forbidden quadrant. This responsiveness unsettled analysts who had long relied on the predictability of spectral behaviour. A few theoretical groups noted that the spectral signature bore a faint resemblance to interactions seen when particles pass through regions of altered field density. In controlled laboratories, certain exotic particles emit narrow transient wavelengths when moving through structured environments. These analogies were fragile and incomplete, but they provided a starting point for speculation. Something in the quadrant might be affecting the object's surface in a way unknown to classical chemistry. Another set of researchers suggested the signature resembled a phenomenon observed only in high-energy astrophysics light, modulated by weak interactions with hypothetical particles. These proposals drew on speculative frameworks that attempt to describe how unseen fields might influence photon behavior. Though the connection remained uncertain, the unusual spectral band fit awkwardly, yet intriguingly into this context. It behaved like a subtle distortion, rather than a direct emission. As data accumulated, the spectral line displayed a rhythm that complemented the faint pulses identified earlier. It brightened and dimmed with a timing that did not fully align with the object's rotation or its changing distance from Earth. Instead, it seemed to follow shifts in the acceleration curve. Analysts noted that each time the acceleration increased slightly, the spectral feature sharpened. Each time the push stabilized, the band softened. The synchronous behavior suggested an interaction rather than a property inherent to the object. Some investigators described the effect as the spectral equivalent of stress marks forming on a surface under unseen pressure. To better understand the anomaly, researchers turned to full-spectrum imaging. These instruments revealed faint halos around the object, delicate rings of scattered light that did not resemble ordinary cometary scattering profiles. The halos carried structural asymmetries subtle but repeatable, pointing toward the forbidden quadrant. Their orientation suggested that the object was travelling through a region that imposed direction-dependent effects on its surface. These halos seemed to form as the object brushed against something invisible yet structurally defined. Additional analysis revealed that the mysterious emission responded to changes in the object's velocity. When 3 Atlas crossed a particular threshold, the spectral line drifted, slightly shifting in frequency, as though stretched by an interaction not governed by standard Doppler effects. The shift was too precise to be noise, yet too small to map cleanly onto known physics. The behavior challenged the notion that space between stars was uniform. Instead, the signature suggested gradients in the medium gradients too subtle for previous missions to detect. Some astrophysicists proposed that the quadrant might contain pockets of exotic particles left behind by early cosmic events. These particles, if they existed, could create narrow wavelength interactions when matter passed through them at certain velocities. Though no direct evidence of such particles had ever been found, the mathematical scaffolding supporting their existence remained intact. The spectral anomaly breathed new life into these old considerations. Other teams explored whether the signature might be a sign of a deeper quantum interaction. In advanced simulations, a few quantum field models produced similar spectral distortions when objects moved through regions where the field exhibited anisotropic tension. This idea suggested that the quadrant might contain wrinkles in quantum space, delicate variations shaped by ancient turbulence or primordial transitions. While speculative, the simulated results aligned eerily with the observed data. Further complications arose when ultraviolet monitoring equipment detected faint harmonics emerging from the same region of the spectrum. These harmonics did not match any known molecular transitions. Their spacing hinted at oscillations intrinsic to the environment, not the object itself. Combined with the repeating pulses and acceleration anomalies, the harmonics intensified the sense that the quadrant housed structures woven into space structures so faint that only interstellar objects moving with specific velocities could reveal them. Researchers working with photometric time series data noted that the brightness variations in the spectral line followed patterns reminiscent of optical interference. They speculated that if the region contained layered textures, Perhaps variations in field strength or density, then light reflected from the object, might carry faint imprints of those layers. The effect would resemble ripples on a pond, revealing the shape of an unseen current. The scientific community, confronted with these layered peculiarities, found itself unable to rely on any single interpretation. The spectral light resisted categorization, standing at the crossroads of chemistry, physics, and cosmology. It acted not as an emission, but as a reaction, a subtle response to something woven into the quadrant. The object moved through space like a needle passing through fabric, pulling a trace of hidden structure to the surface. In the final analyses of this phase, researchers recognized that the spectral anomaly was not a standalone feature. It belonged to a growing constellation of signs, the acceleration, the pulses, the vector that collectively formed a pattern. Each piece reinforced the others, pointing to a region of space that did not behave as emptiness should. The spectral light, delicate yet persistent, had become a beacon, illuminating the edges of a mystery whose full shape had not yet come into view. The strange thermal envelope surrounding 3I Atlas emerged not through dramatic heat signatures or violent bursts of energy, but through a quiet mismatch between expectation and measurement. Interstellar objects typically carry cold, inert surfaces shaped by ages of drifting through regions where starlight is faint and energy scarce. Their temperature profiles should follow predictable gradients, governed by distance from the sun surface composition and rotational exposure. Yet when thermal cameras and infrared spectrometers focused on 3I Atlas, the readings shifted in ways that defied these familiar rules. Instead of a smooth arc of heating as it approached the inner system, the object displayed a patterned envelope of warmth and coolness that behaved as though it were interacting with something invisible. The first indication came when infrared data revealed zones of temperature that did not align with the direction of sunlight. Small regions on the surface glowed with slightly elevated heat, not enough to suggest active outgassing or internal reactions, but enough to stand out from the expected uniform cold. Other areas appeared cooler than environmental modelling predicted, as if the object were being shielded or insulated by a force with no visible source. The distribution formed a mosaic, a delicate tapestry of thermal anomalies that shifted slowly as the object rotated. Scientists checking the readings searched for mechanical explanations. They speculated about surface cavities, compositional variations, subsurface ice pockets, or reflective mineral clusters. But none of these ideas could fully explain the pattern. Natural comets show irregular heating, but those variations correlate with topography and rotation. In contrast, the thermal envelope around 3I Atlas maintained its structure even as the object turned. The pattern behaved like a static imprint rather than a surface feature. It clung to the object regardless of orientation, as if anchored to the space through which the body travelled rather than the body itself. Researchers examined whether the heating could originate from faint jets invisible to standard imaging, but thermal modelling required energy levels higher than any known sublimation process could support at the object's distance. The absence of accompanying dust signatures dismissed this idea as well. If jets existed, they would leave trails detectable by photometric analysis. None appeared. The thermal anomalies stood alone, unaccompanied by physical evidence of material release. As the anomaly persisted, a subset of researchers turned to environmental explanations. They considered whether the forbidden quadrant contained subtle fluctuations in radiation density. If the object were passing through regions with uneven distributions of high-energy particles, its surface might display irregular heating. But radiation detectors scanning the region found nothing unusual. The background particle flux remained stable, typical for that part of interstellar space. No external radiation source explained the pattern. Further investigations revealed that the thermal envelope shifted in tandem with the object's acceleration. Each time the unexplained push increased, the warm regions intensified slightly. And when the motion stabilized, the pattern softened. This synchrony implied a correlation between the invisible force acting on the object and the thermal behavior shaping its surface. The heat did not arise from internal processes. It responded to something in the environment, something that exerted influence with remarkable precision. One research group studying exotic field interactions suggested that the thermal anomalies resembled the effects produced when objects move through regions of altered field tension. Laboratory-scale experiments have shown that variations in certain hypothetical fields can influence energy distribution on surfaces, creating temperature patterns without direct heating. These interactions remain speculative, but the resemblance intrigued scientists. Perhaps the quadrant contained gradients in a field not accounted for by conventional physics gradients. that imparted heat through subtle exchanges rather than radiant transfer. Another theoretical possibility emerged from quantum field studies. Under certain models, the vacuum itself contains fluctuating structures that can interact with matter on extremely small scales. If 3I Atlas were moving through a region where these vacuum structures were slightly misaligned, the interaction might produce localized temperature differences. These differences would not radiate outward as heat usually does. Instead, they would appear as pockets of shifted energy, visible only through sensitive measurements. Although highly speculative, the behavior matched the envelope's oscillating nature. Scientists also noticed that the envelope did not simply attach itself to the object. It extended outward in a thin halo visible through infrared scattering analysis. This halo shimmered like an atmospheric layer, though no atmosphere existed. It behaved more like a shell of energy surrounding the body, responding to forces that instruments could not detect. When mapped over time, the halo revealed faint distortions that aligned with the pulses identified in earlier data. The shapes and intensities formed a rhythm and oscillating dance that connected thermal fluctuations with the invisible patterns embedded in the quadrant. Observations from space-based telescopes added another layer of complexity. These instruments detected microvariations in the halo's thickness variations that seemed to follow the object's distance from certain coordinate axes in the quadrant. Even small shifts in trajectory altered the envelope's structure. This sensitivity suggested that the object was passing through a region whose geometry contained features too subtle for gravitational or electromagnetic instruments to register. The thermal envelope acted like a tracer outlining these hidden structures through changes in heat distribution. Researchers studying the motion of interstellar dust grains offered another perspective. Dust passing through the quadrant displayed slight deflection patterns, in archived data deviations too small to draw conclusions from at the time. Now those deviations seemed relevant. They hinted that the quadrant might influence small particles through mechanisms separate from gravity or electromagnetism. If such a mechanism existed, 3I Atlas, with its low mass and high sensitivity, would be an ideal probe for revealing its structure. The thermal envelope could be the signature of the object interacting with these mechanisms. Deeper numerical models explored whether tiny fluctuations in dark energy density could influence surface temperature indirectly. Under certain cosmological extensions, small variations in dark energy may affect the vacuum state surrounding an object, altering the local distribution of energy in non-thermal ways. Though purely theoretical, these ideas found unexpected resonance in the thermal data. The envelope behaved as though shaped by an external field that responded to the object's velocity and direction, not by internal heat sources. Some researchers proposed that the envelope was not simply a reaction. It might serve as a tool for examining the quadrant's properties. By studying the envelope's deformation, scientists could map gradients in the hidden structures that shaped it. Early maps revealed a faint pattern of directional bias, a subtle guiding framework that seemed to point toward deeper regions of the quadrant. This framework aligned with the acceleration vector, reinforcing the notion that the forces driving the object were intertwined with the region's concealed architecture. The most unsettling interpretation came from a subset of specialists analyzing hypersensitive photon-matter interactions. They suggested that the envelope resembled the thermal signature produced when matter passes through areas where space-time tension fluctuates on extremely small scales. In such areas, the vacuum can behave unpredictably, altering the way energy settles on surfaces. If 3I Atlas were moving through such a region, the thermal envelope would represent not heat in the traditional sense, but a trace of altered space-time dynamics. Whatever the cause, the envelope signaled that the object was no longer merely drifting through space. It was interacting with environment, an environment with structure rhythm and hidden complexity. The envelope marked 3I Atlas as a moving witness to forces not yet fully understood, forces that might reveal themselves fully only when the object reached deeper into the quadrant. Scientists watching this development understood that the thermal anomaly was not a side effect. It was a message, not one spoken in words or signals, but in the delicate language of heat and motion, a language shaped by forces lying beneath the visible world. And as the envelope intensified in sync with the object's acceleration, the scientific community realized that 3I Atlas was entering a region where the familiar rules of physics were about to be tested in unprecedented ways. Instruments turning toward the unknown mark the moment when the anomaly surrounding 3I Atlas shifted from a quiet curiosity to a coordinated global investigation. What began as isolated discrepancies in spectral and thermal data soon demanded the attention of nearly every major observatory on Earth and in orbit. Telescopes that typically operated on rigid schedules planned months in advance began adjusting their priorities. Instruments designed to monitor transients, exoplanets, pulsars, or distant galaxies redirected their gaze toward a single small visitor, drifting through the solar system with inexplicable behavior. The first wave of redirection came from wide field surveys. These observatories broadened their imaging cadence, capturing the object more frequently, to refine its acceleration curve. Their data, once purely positional, expanded into multi-filter photometry to track subtle color variations correlating with the unusual thermal envelope. Analysts soon realized that the object's brightness fluctuations contained far more structure than earlier thought. Tiny oscillations hidden beneath ordinary photometric noise sharpened when processed through enhanced algorithms. These oscillations mirrored the repeating pulses detected in radio data, reinforcing the idea that the object was responding to environmental forces. Space-based instruments offered sharper clarity. The James Webb Space Telescope, initially not scheduled for near-solar system observations, dedicated brief windows to examine the object's infrared characteristics. JWST's unrivaled sensitivity exposed fine-grained distortions in the halo surrounding 3I Atlas. These distortions suggested that the halo was not a simple envelope, but a layered structure, with each layer reacting differently to the object's changing acceleration. The patterns behaved as though the object were traveling through gradients of invisible tension, each gradient leaving its imprint on the halo's shape. At the same time, ground-based, adaptive optics systems produced images with surprising resolution. The extended thermal traces trailing behind the object appeared to ripple slightly, forming faint wave-like structures aligned with the forbidden quadrant. These ripples did not resemble dust tails or gas flows. They looked like the signature of an object moving through a medium too subtle for traditional measurements to capture, as if drifting through the edge of an unseen current. Radio observatories intensified their efforts as well. Facilities such as the Very Large Array and the Square Kilometre Array began tracking the pulses beneath the noise with unprecedented precision. Their deeper analysis revealed that the pulses carried fine temporal modulations, minute shifts in timing, that correlated with the object's position along certain coordinate axes in the quadrant. These modulations suggested that the environment contained periodic structures like faint echoes left behind by processes occurring long before the solar system formed. Researchers operating gravitational detectors also joined the investigation, even though the object was far too small to produce measurable gravitational waves. Their interest lay not in the object itself, but in the possibility that its motion might interact with large-scale space-time irregularities. Sensitive detectors picked up faint ripples, tiny inconsistencies in their data that did not match instrumental noise patterns. The anomalies were subtle, but their timing aligned disturbingly well with the pulses detected by radio instruments. Though far from conclusive, these findings hinted that the quadrant might contain shallow fluctuations in space-time curvature, detectable only through the cumulative effect they imposed on multiple types of instruments. The scientific community responded to these hints with increased coordination. Networks that once shared data only occasionally now exchanged information constantly. Observatories adjusted exposure times to capture more nuanced photometric curves. Spectrographs refined their calibration routines to isolate faint wavelength distortions. Infrared and ultraviolet instruments synchronized their observation schedules to detect crossband correlations. The investigation had evolved into a collaborative effort spanning continents and orbital assets. Mission planners normally distant from observational astronomy became involved as well. They analyzed the object's trajectory with increasing urgency, searching for opportunities to deploy existing spacecraft for closer inspection. Although no deep space missions were positioned ideally for interception, planners examined whether slight trajectory corrections could bring distant probes closer to the object's path. Even a marginal flyby could provide invaluable data about the nature of the forces acting upon it. Back on Earth, researchers began combining datasets across multiple wavelengths, overlaying thermal, spectral, radio-optical and ultraviolet information to construct a multidimensional model of the object's environment. This unified model revealed an unexpected insight. The various anomalies, acceleration pulses, spectral distortions, thermal envelope did not exist independently. They formed a network of interrelated effects, each pointing toward the presence of a structured environment within the forbidden quadrant. The quadrant was not simply empty space. It behaved as though it contained a substrate, a hidden architecture that interacted with the object in complex ways. The most surprising discovery came from deep scanning magnetometers aboard orbiting satellites. These instruments detected faint deviations in magnetic field readings, not strong enough to indicate magnetic objects, but subtle enough to suggest that the surrounding space carried slight irregularities. The deviations aligned with the object's path, forming patterns that resembled gentle twists within the magnetic field. Though too small to affect planets or large bodies, these twists could influence objects as light as 3i Atlas. The detection added one more piece to the growing puzzle. Some teams suggested the region contained remnants of ancient cosmic events, shells of structured energy left behind by processes that occurred shortly after the birth of the universe. Others considered the possibility that the quadrant accumulated tension from large-scale galactic flows, producing fine gradients that ordinary matter could not detect. A few more radical ideas proposed that the quadrant represented the outer boundary of a subtle transition in space-time characteristics similar to how atmospheric layers behave on planetary bodies. Regardless of the interpretation, one fact became clear: 3i Atlas was moving through a region where the universe behaved differently. The instruments once pointed elsewhere now focused intensely on the visitor, tracing every fluctuation in its motion. The object had become a probe, silently mapping phenomena that no human technology had been designed to see. The turning of instruments represented not simply a shift in observational priority, but a recognition that the object carried information about a hidden structure woven into the cosmos. Every photon it reflected, every pulse passing through it, every ripple in its halo acted like a message encoded in the language of the universe. The world of astronomy watched in unified anticipation, aware that the deeper 3i Atlas drifted into the quadrant, the more the invisible architecture would be revealed. And as instruments continued to realign, the object's acceleration grew more pronounced, as though answering a call from something waiting in the depths of the region ahead. Space-time ripples in the data first appeared as microscopic irregularities buried inside streams of precision measurements, variations so slight that only enhanced correlation algorithms could detect them. These fluctuations did not resemble gravitational waves, nor did they match the soft jitter typical of instrumental noise. Instead, they carried a faint coherence, a pattern, repeating at intervals subtly connected to the object's acceleration. When researchers began layering data from multiple observatories, a quiet realization took shape. Something in the space surrounding 3i Atlas was oscillating, pressing its rhythm into the fabric of the readings, as though the region itself possessed an internal pulse. Analysts examining the ripples noted that they emerged only when the object passed through specific coordinate thresholds within the forbidden quadrant. Instruments scanning unrelated areas of the sky detected no such anomalies. This localization strengthened the idea that the ripples were environmental, not instrumental. They were tied to the quadrant, not to Earth or to any particular telescope. The pattern grew clearer as datasets from radio arrays, optical telescopes, and deep-field observatories converged. Each dataset, when synchronized with time correction protocols, revealed the same subtle distortion, a faint bending of expected values, as if space-time in that area had adopted a slightly different cadence. The ripples had a peculiar structure. Instead of the sweeping curves characteristic of known space-time disturbances, they manifested as short, tight fluctuations, micro-variations that altered the trajectories of photons passing through them. Geometry-sensitive instruments detected slight delays in transit times, delays too consistent to dismiss. These delays aligned themselves along narrow paths that extended forward from the direction the object was traveling. It was as if the object were moving through fine threads of distorted space-time, each thread vibrating under conditions yet to be understood. Research teams specializing in advanced gravitational modeling began probing deeper. They attempted to reconstruct the ripples by feeding the data into curvature-sensitive algorithms, usually reserved for analyzing gravitational lensing or black hole environments. To their surprise, the programs produced maps with faint contours, shadows of curvature gradients, too subtle for standard devices, but present nonetheless. These contours did not resemble known gravitational effects. They behaved more like irregularities in space-time tension, small pockets, where the fabric of the universe flexed in ways that defied classical expectations. A few theoretical groups noted that the ripples exhibited similarities to predictions made in certain fringe cosmological models. These models proposed that remnants of ancient cosmic transitions could leave imperfections in space-time, tiny residues scattered throughout the galaxy. Normally, these residues would remain undetectable, drowned beneath the overwhelming influence of nearby stars and planets. But interstellar objects with minimal mass drifting through delicate regions of the void might reveal these imperfections through subtle distortions in their motion and reflected signals. The ripples around 3I Atlas aligned disturbingly well with such predictions. Other researchers explored an alternative possibility that the ripples were a product of the object interacting with a gradient in an unseen field. Some extensions of quantum field theory allow for small-scale fluctuations in the vacuum itself, where energy density varies slightly across space. If 3I Atlas were moving through such a region, the fluctuations could imprint themselves on the data as periodic shifts modulating the trajectories of particles and photons alike. Under this interpretation, the quadrant might house a layer of vacuum variation, a hidden stratum woven into the cosmic background. The idea gained traction after deep space magnetometers detected faint oscillations synchronized with the ripples. These oscillations were minute but persistent, suggesting that the region contained multiple intertwined effects, all responding to the same underlying structure. The synchronization hinted that the anomalies were not random phenomena layered atop each other. Instead, they reflected different aspects of a single unified cause, something that influenced geometry, magnetism, and energy distribution at the same time. Space-time analysts studying long-term pulsar timing arrays introduced another perspective. In the past, they had observed slight timing disturbances when signals passed through certain distant regions of the galaxy. Most of these disturbances were attributed to plasma clouds or gravitational scattering. However, a few unexplained cases shared structural similarities with the ripples now surrounding 3I Atlas. The comparison sparked renewed interest in whether the galaxy contained pockets of altered space-time quiet regions, where ancient dynamics had left behind faint but persistent imprints. As the object continued its journey, the ripples intensified slightly. They did not grow chaotic or unstable. Instead, their amplitude increased in proportion to the object's acceleration, mirroring the same alignment found in earlier anomalies. Researchers noted that the ripples seemed to anticipate the object's movement shifting just before the object entered new coordinates. This anticipatory behavior resembled the way waves ripple outward, ahead of a moving hull, except here the waves existed not in water but in the structure of space-time itself. Simulations attempting to replicate the ripples revealed something unexpected. When placed into a model of standard space-time, the ripples dissolved almost immediately. But when introduced into frameworks involving layered curvature regions, where space-time shifted gradually between slightly different properties, the ripples persisted. These simulations suggested that 3I Atlas was moving through a transitional band, a place where the cosmic fabric gently changed its character. Such a transition would be too subtle to affect large bodies, but objects with minimal inertia could feel its influence, revealing its presence through small deviations. Instruments designed for precision timing uncovered yet another layer. The ripples carried harmonic overtones, faint echoes, that spilled into higher frequencies. These harmonics provided strong evidence that the ripples were not artifacts of instrumentation. Instead, they behaved like natural oscillations originating from the environment. Their structure hinted at a regularity more complex than random noise, a regulated hum embedded within the quadrant emerging only when disturbed by motion. A few cosmologists proposed that the ripples might indicate a region of spacetime undergoing slow relaxation, a process in which curvature adjusts over vast timescales following ancient cosmic events. These events could include the settling of early universe defects, or the remnants of gravitational interactions between massive structures long since dispersed. Under this interpretation, the quadrant represented a historical archive, a place where space-time preserved a faint memory of its origins. Though no single theory dominated, a consensus began to form. The ripples were real, persistent, and intimately tied to the region through which 3I Atlas moved. They suggested that space-time in the quadrant was not uniform. It contained layers, tensions, and resonances that ordinary instruments had failed to detect until the object passed through them. The discovery reframed the anomaly not as an isolated quirk, but as part of a broader phenomenon hiding in the depths of cosmic space. As scientists continued to map the ripples, they understood that they were witnessing the behavior of spacetime in a state rarely observed. The universe was revealing a part of itself normally concealed behind the monotony of apparent emptiness. And as 3I Atlas pressed deeper into the quadrant, the ripples grew clearer, offering the first tangible glimpse of a hidden architecture, stretching far beyond human anticipation. Acceleration Phase 2 begins not with a violent surge nor with any dramatic burst of activity, but with a subtle curvature in the data and inflection so gentle that only long-duration plots reveal its true significance. For weeks, scientists had tracked the steady, inexplicable push acting on 3I Atlas, a quiet force that defied familiar physics, yet maintained consistent strength. Then, without warning, the slope of the acceleration curve shifted, not slowly, not gradually. It bent into a new form as though the object had crossed an invisible threshold and entered a deeper layer of whatever phenomenon governed the forbidden quadrant. The first hints came from astrometric measurements processed through ultra-precise timing arrays. Analysts noticed that the object's speed had increased by an amount too large to be a continuation of the previous trend, yet too controlled to be random. A fresh gradient had appeared. The magnitude of the acceleration nearly doubled while its direction tightened even further toward the vector that had troubled researchers since the earliest observations. In the centres, monitoring the trajectory screens displayed curves arching upward with a new clarity. The numbers no longer drifted, they marched. This change unsettled researchers not because of the raw acceleration, but because of what accompanied it. All the previously identified anomalies responded as if coordinated. The faint pulses buried in the radio noise sharpened. The spectral distortions gained structure, developing a slightly wider bandwidth and a more defined peak. The thermal envelope thickened, forming an even more pronounced halo around the object. Each anomaly acted in concert, shifting in ways that mirrored the acceleration jump. It was as if the environment had changed state, transitioning into a new mode, and the object was moving through layers of an unseen field that intensified as it advanced. One of the most striking developments came from the timing of the pulses. They began to compress, their intervals shortened, forming a cadence that hinted at an emerging rhythm. Analysts studying these shifts observed that the timing followed a precise mathematical relationship to the second phase of acceleration. This behaviour suggested not that the pulses were emitted by the object, but that the environment itself was reacting to the object's presence with increasing sensitivity. In space weather monitoring centres, instruments designed to track cosmic radiation detected mild fluctuations that traced the object's motion. These fluctuations were not typical particle bursts. They were faint depressions in the local energy field, like soft voids moving in tandem with the object. The pattern resembled the effect of a body drifting through a medium with subtle resistance, yet resistance implied a substance. None existed, not in any detectable form. As acceleration phase 2 unfolded, researchers revisited high-energy models that described how objects might behave when passing through regions with anisotropic vacuum tension. These models had always been theoretical, rooted in the idea that quantum fields might stretch or compress at microscopic levels across vast cosmic areas. According to certain formulations, an object moving through such a region might experience an effective push not from matter or radiation, but from gradients in the vacuum state itself. Such forces would not resemble the familiar push and pull of classical physics. They would manifest as quiet, consistent accelerations, precisely the type observed in the first phase. But phase 2 presented a new complication. The increase in acceleration followed a curve characteristic of threshold transitions observed in nonlinear systems. In complex environments, crossing specific boundaries often leads to abrupt changes in dynamic behavior. These transitions appear in fluid dynamics, plasma turbulence, and certain quantum systems. For an interstellar object to display similar behavior meant that 3I Atlas had likely entered a region where the underlying properties of space shifted in discrete steps. Astronomers attempted to identify the boundary the object had crossed. They analysed the object's position relative to known structures, dust density maps, magnetic field alignments, gravitational potential gradients. None aligned with the moment of transition. Instead, the timing matched an intersection, with a coordinate plane defined only in theoretical simulations. In these simulations, certain regions within the forbidden quadrant produced layered responses when objects passed through them. These layers acted like stacked sheets of slight curvature differences invisible to ordinary matter, but capable of influencing trajectories under very specific conditions. The transition into phase 2 seemed to correspond with the first crossing of these simulated layers. If true, the quadrant's hidden architecture was not merely a smooth gradient, but a stratified environment. Each layer might represent a distinct configuration of space-time tension, a relic of long-forgotten cosmic events that had left behind regions where the vacuum behaved with faint but measurable structure. In support of this idea, the thermal envelope displayed a new behavior, a trailing wake. Infrared sensors recorded faint fluctuations extending behind the object, forming a slowly shifting filament. This filament did not resemble dust gas or plasma. Instead, it appeared to be a deformation in the envelope itself, as if the object was dragging behind it a ripple in the environment, like a boat shaping a wake upon entering faster-moving water. The wake's rhythm matched the compressed pulses and the drift of the ripples in space-time detected earlier. The acceleration's second phase intensified another signature oscillations in the object's apparent brightness. These oscillations grew smoother, more coherent, acquiring a pattern that resembled interference between two overlapping rhythms, one from the object's rotation, the other induced by the environment. When analysts subtracted the rotational component, a remaining signal appeared. This residual pattern did not match any internal property of the object. It matched the environment. The light reflected from 3i Atlas now carried the imprint of the region itself. More sophisticated simulations revealed that Phase 2 acceleration produced small curvature artifacts in the object's projected path. These artifacts resembled tiny bends, turning points within turning points, subtle deviations that accumulated only under extreme magnification. In one sense, these artifacts suggested the presence of multiple forces. In another, more sobering interpretation, they implied that the same force operated in varying intensities, shaped by spatial structure, invisible to standard physics. Some research groups speculated that the acceleration's intensification was not driven solely by environmental factors. They proposed that once the object entered the quadrant's deeper layers, it triggered a feedback loop. The region responded to the object's presence, and the object in turn responded to the region's altered state. This interpretation framed the quadrant not as a passive medium, but as a dynamic environment capable of interacting with drifting matter. The idea carried profound implications. If the quadrant contained responsive features, structures that modulated their behavior based on passing objects, it suggested the existence of cosmic mechanisms far more intricate than previously imagined. These mechanisms might have evolved naturally shaped by ancient gravitational flows or primordial field interactions, or they might represent fossilized remnants of processes occurring in the early universe, preserved across epochs. Regardless of origin, the second phase of acceleration revealed that 3i Atlas was moving through a region that did not behave like empty space. It behaved like a layered landscape, a place where forces emerged differently depending on depth, direction, velocity, and the object's own physical properties. As the acceleration continued to climb, analysts realized that Phase 2 might not be the final stage. The object showed no signs of stabilizing. Its trajectory tightened further. The environment responded with increasing precision, and the quadrant, once a mathematical curiosity, now appeared to hold its own form of gradient guiding the object deeper into its structure. 3i Atlas had crossed an unseen boundary. What lay ahead would challenge the limits of every existing model of cosmic behavior. Yet the object continued onward, quiet and steady, pulled by forces the universe had concealed until this precise moment. Mathematics break under pressure not because equations fail suddenly, but because the assumptions beneath them begin to fracture when confronted with patterns they were never designed to hold. For decades, orbital mechanics has rested on a foundation of stability, gravity's elegance, inertia's consistency, and the predictable behavior of objects drifting through the interplanetary void. Yet, as 3i Atlas advanced deeper into the forbidden quadrant, the models tracking its motion began collapsing with unsettling regularity. Calculations that once converged cleanly now diverged with small perturbations. Simulations that should have produced graceful arcs instead dissolved into chaotic spirals. The mathematics long trusted started to pull apart at the seams. The first cracks appeared in classical trajectory solvers. These solvers tracked the object's path with precise error margins, updating predictions as new measurements arrived. But once the acceleration entered its second phase, the solvers began failing their own consistency checks. Tiny changes in input values far smaller than instrumental noise produced disproportionately large swings in predicted positions. Analysts attempting to refine the models found themselves confronted by sensitivity levels that exceeded any known orbital scenario. It was as if the space through which the object traveled had become numerically unstable. Teams shifted to higher-order gravity models incorporating relativistic corrections. These too began showing signs of strain. Under standard conditions, relativistic adjustments provide slight refinements, microscopic tweaks in curvature effects. But now, those same adjustments amplified the volatility of the simulations. The relativistic terms interacted strangely with the object's observed acceleration, magnifying discrepancies instead of reducing them. The math behaved like a finely tuned instrument struck by an unexpected resonance, vibrating in ways that revealed structural weaknesses. Some analysts turned to nonlinear dynamical models, the kind used to study chaotic systems like planetary resonances or unstable asteroid clusters. These models, built for complexity, should have handled irregularities gracefully. Instead, they buckled. Even the smallest acceleration variations pushed the models into unpredictable territory. Trajectories collapsed into chaotic attractors, producing patterns that bore no resemblance to the object's measured path. Attempts to stabilize the models with damping algorithms only highlighted the instability the mathematics could not express the object's motion without spiraling into incoherence. This widespread failure forced theorists to examine the underlying equations themselves. The problem did not lie in the tools nor in the data. It lay in the assumptions woven into the mathematical infrastructure assumptions about the uniformity of space, the consistency of gravitational influence, and the absence of directional bias in the vacuum. If any of these assumptions were violated within the quadrant, even subtly the equations would respond by collapsing. And that was exactly what began to unfold. Geometric models mapping spacetime curvature provided further insight. When researchers plotted the object's trajectory against curvature fields derived from general relativity, the alignment faltered. The curvature maps did not match the behavior of the object. Instead, the trajectory suggested interaction with curvature components, that standard relativity does not account for components too faint to be included in current equations, yet powerful enough to influence motion. Some referred to these discrepancies as shadow curvature regions, where the geometry of spacetime might be slightly offset from textbook expectations. Quantum-informed models introduced another layer of complexity. These models attempted to merge classical trajectories with vacuum fluctuations, exploring how quantum variations might shape macroscopic motion. But even these sophisticated frameworks began collapsing. The variance parameters inflated into numerical instability. The predicted paths fractured into countless branches, none matching the object's observed movement. It was as if the quadrant's vacuum tessellated itself into patterns the models could not represent. Despite these failures, a few intriguing results emerged from the chaos. In certain simulations, when analysts introduced hypothetical gradients, variations in vacuum density, small changes in spacetime stiffness, or faint energy anisotropies, the model stabilized momentarily. These stability points lasted only a few cycles, but the effect was striking. It suggested that the object's acceleration might be governed by a field or gradient that normalized its trajectory, under conditions not yet defined by mathematical formalism. Some researchers proposed that the quadrant might contain a layered structure, in which spacetime changes its effective properties similar to how materials change elasticity under pressure. In such an environment, the equations governing motion would shift subtly depending on depth. If 3i Atlas were moving through layers with slightly different curvature rules, then classical models would fail at each transition. The math was breaking not because it was incorrect, but because it was incomplete. Evidence supporting this idea came from a new type of simulation developed for high-energy cosmic phenomena. When those simulations were applied to the data, they produced a faint but consistent result. The object behaved as though traveling through a medium with variable geometric tension. This medium did not exert force like ordinary matter, nor did it resemble magnetic or gravitational fields. Instead, it shaped motion by altering the pathways of least action, the natural flow lines that objects follow through spacetime. Theories emerged proposing that the forbidden quadrant might be a remnant zone from early cosmic transitions. In such a zone, spacetime might retain subtle irregularities left behind by inflationary turbulence or by the settling of topological defects. These irregularities would not break physics. They would simply introduce variations too delicate to affect stars or planets, but strong enough to reshape the path of a small interstellar wanderer. If this interpretation was correct, then the mathematics was not failing at all. It was revealing a deeper structure carved into the universe itself. One group produced a compelling visualization. They mapped the divergence of equations across a 3D grid of the quadrant. The result displayed bands of instability, ribbons of space, where trajectory mathematics fragmented into fractal-like patterns. These ribbons aligned with the object's path, not perfectly, but with enough proximity to hint that the object was following a natural corridor carved into the hidden geometry. a corridor that standard equations could not yet express. The collapse of mathematical frameworks did not signify defeat. It signified discovery. It marked the boundary between known physics and something older, deeper, more intricate. The models were breaking because the quadrant was not empty space, it was a structure. A structure that required new mathematics, new language, new conceptual tools to understand. As 3i Atlas pressed deeper into the region, the failure of the equations became the most important evidence of all. It meant the object had reached a place where the universe no longer behaved according to familiar expectations. The failure of mathematics revealed a truth that no measurement alone could articulate. The quadrant contained layers of reality that current physics was not prepared to describe. And the object was still accelerating. End of script. Sweet dreams.